Here is an example looking at the isentropic efficiency of a compressor. Refrigerant 134A enters an adiabatic compressor, a saturated vapor at 120 kilopascal at a rate of 0.3 meter cube per minute and exits at 1 megapascal. Determine A. The temperature of the refrigerant at the exit of the compressor, if the compressor is reversible. B. The temperature of the refrigerant at the exit of the compressor, if the compressor's isentropic efficiency is 80%. C. Following part B, find the power input in kilowatt. Consistent problem-solving procedures. Identify system process and substance. Fill the table. Find work. Apply first and second law. The system is open if the compressor is at the steady state, steady flow device. The substance is R134A. The process involved in the calculations are the isentropic process, which is required for you to answer part A, and the actual process across the compressor. For part A, since the compressor is adiabatic reversible, we know the process is isentropic. So entropies at the inlet and the outlets must be the same. Let's use the information to fill the table. Two intensive properties were given at the inlet state. So everything else can be found from the table. 120 kilopascal, saturated vapor given. Find everything else at the table. Mass flow rate can be found using the given volumetric flow rate, and the specific volume found. For the exit state, the exit pressure is given at 1 megapascal, as we discussed in class. Since the pressures are determined by the turbo machine's design geometry, the 1 megapascal represents both the actual and the isentropic pressure at the exit state. We know that entropies at inlet and exit must be the same. This gives us two intensive properties to find everything else in the table. From the table, then, we can estimate the exit temperature at the exit state to be 48 degrees. And one thing to note, since the device is a steady state, steady flow device, mass flow rate will stay the same. In part B, we're asked to find the exit temperature if the compressor efficiency is given at 0.8. Use a definition of compressor efficiency. We can see that everything in the equation is known except the value of the actual exit enthalpy. We found the value, solved for it, found the value to be 263.3. Now, with two intensive properties at the actual state known, we can find phase and temperature from the table. We estimate the temperature to be about 53 degrees C. For part C, to find the power input, use the first law for the steady state, steady flow device. Compressor is adiabatic, therefore there's no heat transfer. We know the mass flow rate, inlet-outlet enthalpies, we can then substitute the numbers and find the power input required for the compressor. Because power input is negative, you have a negative number. The power input required for the compressor is negative 0.811 kilowatt.